free response question for you here. Function f has derivatives of all orders for all real numbers. A portion of the graph of f is shown here. This is a graph of f, along with the tangent line to the graph of f at x equals 0. Okay. Selected derivatives, there's second, third, fourth derivative at 0 are given in a table. And this is a Taylor series question. Okay, so that's an interesting way to present the information, but I can get the first derivative, f prime of 0, is, well, they gave me the tangent line, so it looks like it's -2. It's like the first derivative. And then the actual value of the function, f of 0, is 3. So with that 3, the -2 is the first derivative, and then second, third, fourth derivatives, I can write, I could write the fourth degree Taylor polynomial. They only want the third degree one here. So the recipe for writing a series is for third degree, so the third degree Taylor polynomial of something is equal to, this is at x equals 0. Sometimes this is called a Maclaurin series. F prime of 0 times x, that's the first degree term, and then the second degree term is the second derivative over 2 factorial times x squared. If this was at some other place besides 0, then I would have like x minus whatever squared, and so on. Can't forget that. They're not always centered at 0. So that's third derivative, 3 factorial, and then x cubed. All the 3's together. So I just need to plug in my stuff now. So f of 0 is 3, right? I got that from the graph. F prime of 0 is -2. I also got that from the graph. Plus -2x. You can make that minus 2x if you want. Doesn't matter. Same thing. Plus the second derivative is 3 over 2 factorial times x squared, and the third derivative is 23 over 2 over 3 factorial times x cubed. Want to simplify that? Go ahead, but you do not have to. That would be, what, 23 over 12, I guess, if you simplified that. Okay, there's part A. Write the first 3 non-zero terms of the Maclaurin series for e to the x. The first 3 non-zero terms. Okay, so e to the x is equal to, this is a series I'm just supposed to know, right? The e to the x series. So there's the first 3 non-zero terms. And then they want me to write the second degree Taylor polynomial for e to the x times f of x. Okay, well, when I write these, when I want to like multiply one series by another one, remember how we set that up? We make a little grid, like a little times table kind of thing. So since both of these have constants in the front, if you think about what's going to happen, if that's my terms of the e to the x series on this side, and then I have my terms of my f function here, if I go up to x squared here, then I'm going to get x squared terms. Anything past this diagonal in my chart is going to be higher than second degree. So if you see that, that's great, and I'll explain more as we go through. So 3, now I'm multiplying all these by x. 3x minus 2x squared, and 3 halves x cubed. And I don't really need to write that term out because I only need the second degree. So this would be third degree. All this diagonal would be third degree. So I really only need to go to here. That would be 3 halves x squared. And then this next term, if you want to write it out, would be minus x cubed that times that, but I don't need to do that because those are not going to be part of the second degree polynomial, which is what they asked me to write. Okay, so let's combine our like terms. Constant term is 3, so this is the series for e to the x times f of x. The first term is 3, and then I've got 3x minus 2x, and then I've got this. 3 halves and 3 halves is 3, minus 2 is x squared. Lovely. I like putting the dot 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 on there. That's the first 3, or the second degree, right? Second degree, they said. Just have to watch out, make sure you understand. Sometimes they ask for whatever degree, and sometimes they ask for the first however many non-zero terms. So just have to make sure you're doing the right thing. All right, so part C. Let h be the function defined by h of x is equal to the integral from 0 to x f of t dt. Use the Taylor polynomial found in part A to find an approximation for h of 1. Okay, so h of 1 would be equal to the integral from 0 to 1 of the f function. Well, we know the series, so where it says use the Taylor polynomial found in part A, so that's this. So let's see, that's 3 minus 2x. I can start using x's instead of t's here because that turned into a number, plus 3 halves x squared minus, I guess I'm going to simplify that to 23 over 12 x cubed. Why am I using the third degree polynomial here? Because they told me to. All right, so that's equal to this is a pretty easy power rule antiderivative, right? So that'd be 3x minus x squared plus 1/2 x to the third minus 23 over 48 x to the fourth. Yuck. I think that's right. 0 to 1. When I plug 1 into this, I get 3 minus 1 plus 1/2 minus 23 over 48. And that is good. You do not have to simplify that. You can, if you want to. Notice that 24 over 48 is a half. So if you take a half, that's the same. 24 over 48 minus 23 over 48 is 1/48, and 3 minus 1 is usually 2. So 2 and 1/48 is the answer there. 97 over 48. That's another version of the answer. But this is another version of the answer that's correct. Okay? And then part D, it is known that the Maclaurin series for H, that's a little weird that they call it Taylor here and Maclaurin series. I don't know why they're trying to, hopefully that's not confusing to us, but it's weird that they would use both. For real numbers, that it converges. It is also known that the individual terms of the series alternate and decrease in absolute value. Oh, that means I can use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.45. So the alternating series error bound says that the actual value differs from the approximation by not more than the next term. So the next term in this, let's see, we never made the fourth degree term. This is using the third degree. So the fourth degree term would be, let's see, the absolute value of the fourth derivative at 0 over 4 factorial times what are we plugging in? 1? Right? So that is equal to the fourth derivative is 54 over 4 factorial is 24. Oh, wait a minute. What am I plugging these into? This is, I need to find the next term. Oh, I forgot to do, if we're doing the h function, that h function, it has things that's inside this integral. Oh dear. So let's get rid of that. So I need to take the antiderivative of that. So the next term would have been dot, dot, dot. It would have been this 54 over 24 x to the fourth. Right? That would have been the next term. And let's see, what's 54 over 20? Well, I'm just not going to simplify it. So the antiderivative of that would be 54 x to the 5 over 24 times 5. So this is the thing that we need to plug the 1 into. Like, that's the next term, because we used this in our approximation. So the next term is the antiderivative of that. That's a little tricky. So that's going to be this, and you could certainly leave it like that. That's totally fine. If you want to flex your muscles and do some reducing, let's see, both of these are divisible by 6, I guess, so that's 9, and 6 goes into that 4 times, so that'd be 9 over 20. And hey, that's 0.45. That's what we were supposed to do there. All right.